Hey, right back at you again with section 9.2. I might end up recording this one in a couple of separate videos. We'll see how this goes, but I want to make sure I get through this in a reasonable amount of time. I don't want to have you sit here for more than 20-25 minutes at a time taking in these videos, because I know there's a lot of information to process. So 9.1, just a little while ago, we looked at the basics of combinatorics, the study of counting things. And we talked about basic probability. How do you determine the likelihood of a certain outcome given a certain range of possibilities? The probability, as we saw, was the number of times an event occurred divided by the number of possible outcomes in total in the sample space. That gave you a probability for equally likely occurring events. We're going to advance our knowledge of combinatorics a little bit in this section, talking about some rules and some tools that will help us count events in a little more complicated fashion. We're going to look first at the multiplication rule, which has to do with looking at events where there are multiple stages in the process. So if there's step 1, there's a certain number of possibilities, and then step 2, there's a certain number of possibilities. And we'll talk about counting different outcomes in that context. And then we'll look at a special application of the multiplication rule that comes in when we look at possibility trees. A possibility tree is a really nice tool for kind of encapsulating all of the possible outcomes in a complicated process involving the multiplication rule. So at its very basic, multiplication rule is the following. The multiplication rule says if you've got a multi-step process, if we have a process that involves, let's see, I want to make sure I'm want to make sure I'm looking at using the notation that your book uses. It involves, let's say, k steps, and the ith step can be done in n sub I ways. So we're going to take 1, 2, 3, 4, up to k steps to complete our process. And at each step, there are n sub I ways of doing that step. Then the number of ways of completing the process is, well, it's going to take k steps, and each step is going to give us a certain number of outcomes. So after the first step, we have n1 possible outcomes, because that's the number of ways we can do the first step. But for each of those possible outcomes, the second step can be performed in n2 ways, and we can mix and match any way we want to. So the n1 ways of doing the first step can be combined with each of the n2 ways of doing the second step, yielding n1 times n2 ways of doing the first two steps. Does that make sense? Make sure you're understanding. Pause the computer and make sure you're understanding that idea before you go further. N1 possibilities for the first step times N2 for the second step. And it continues. Adding on the third step, for each of the N1 times N2 ways of doing the first two steps, we have N3 ways of doing the third step. So we take another product, and so forth. Multiplying all of these together up to n choose k, or n times n sub k rather. So if this you can see why this is called the multiplication rule, because we're multiplying all of these together. So if we have ni ways of doing each of the ith steps, the product of all of the ni's is what gives us the number of ways of choosing or of completing the whole process. And there are some assumptions here. Notice we're not looking at probability, by the way. We're not assuming the likelihood of each of these outcomes. We're just counting them. So this is getting back to the basics of combinatorics, just counting and not computing probabilities yet. We'll get to probabilities in a little while here. This is just a way of enumerating all possible outcomes. So an example of this, for instance, would be when we're looking at character strings. Certain constraints on or rules that govern the way that character strings can be put together. Your textbook goes into some specific examples, but I'm going to look at a couple here. So let's suppose, for instance, so how many ways can the letters in the word central be rearranged? So we have 7 letters in the word central, and each of the letters is distinct. I chose this example or this word specifically because they're all distinct, and we don't have to worry about distinguishing 2 different E's from each other. So how many ways can we rearrange the letters in the word central? Now, I claim that we can apply the multiplication rule directly, and this is because we can always pick as the first step in the process what's our first letter. In the second step of the process, we pick our second letter. The third step, we pick the third letter, and so forth. So the first step is to pick the first letter, and we can do this. We need to know what NI is, N1 rather. We need to know how many different ways there are picking the first letter. Well, we haven't made a choice yet, but from among the 7, we can pick any one of them. There are 7 choices for picking the first letter. For picking the second letter, the second step in the process, this is a little more subtle. It might look as though there are 7 choices, but we've already made, if we're in the second step, we've already performed the first step. And so there are only 6 ways, whereas N1 was 7. By the time we get to the second step, there are only 6 ways of picking the second letter. So N2, the number of ways we can do this second step is actually 6. N3, the number of ways of picking the third letter is going to be 5 because we've already made the first and second choices, leaving us with only 5 letters to choose from. Notice, we don't know which letters they're going to be. That depends on the choices we made previously. However, we know that we are only going to have 5 no matter how we perform the first 2 steps. Similarly, the number of ways of picking the fourth letter will be 4. The number of ways of picking the fifth letter will be 3. The number of ways of picking the sixth letter will be 2, because at that point we'll have exhausted all but 2 letters. And then we are effectively forced, in the last letter, to pick only the one. There's only 1 letter left, so there's only 1 way to do it. Multiplication rule now says that to find the number of ways to complete this process, we take each of these numbers and we multiply them together. So the letters can be rearranged in 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 7 factorial ways. And I happen to remember that 5 factorial is 120, times 6 is 720, times 7 is going to be what? 720 times 7, 499 plus 5,040 different ways. So there are 5,040 different ways of rearranging the letters in the word central. We got that from the multiplication rule. This is also an example of another version of the multiplication rule, which is called permutations, which looks at what are called permutations. Your textbook talks about, make sure you, by the way, pause the video and make sure you understand this example before we go any further. So we're going to take it just a little bit further and look at more general permutations in just a moment. So, again, a permutation takes this idea of this sort of process, goes one step further. So, a permutation of R objects from among N objects, just to be clear, that's another number of objects. A permutation of R objects from among N objects is really just a choice. You have a bag of N objects and you reach in and you grab out R of them. is a choice of R objects from the n available. And the number of permutations, the number of permutations of R objects from among n, so P of nr is the number of such permutations. And it turns out that the formula for this is given by n factorial divided by n minus r factorial. And my marker is about to run out, so I'm going to go ahead and refill it in real time here. Fortunately, my garbage can is right here. Time me. How long is this taking? Done. All right, we're ready to continue. An example of applying permutations. This example we looked at with rearranging the letters in the word central is actually a permutation. This is a permutation of 7 objects from among 7. The choosing of 7 objects in a certain order from among the 7 available. If we wanted to look at a related but different example to this one, what if we were given the letters in the word central? So, example, from the letters in central, how many ways, here's the question, how many ways can we pick 4 of them? So our collection has 7 objects in it, so n is going to equal 7. And we're being asked to pick 4 of them, so r is going to equal 4. So the answer is going to be p of 7, 4. And our formula here, by the way, I'm going to talk about where this formula comes from in a moment. Our formula here says to take 7 factorial and divide by 7 minus 4 factorial, which is 7 factorial divided by 3 factorial. Now we could just do this directly by computing what 7 factorial is and dividing by 6, but a better way that generalizes is to write out the top and the bottom, because we're going to have a lot of cancellation, and that makes our work a little easier. Writing out the top and writing out the bottom, we see the 3, the 2, and the 1 will cancel, and we're left with, what here? 6 times 20 is 120 times 7, 700, that's 840. So instead of having to work with 5040, which we might not have had on hand if we hadn't done this problem just a moment ago, we can do this with a little bit of cancellation, a little bit of clever arithmetic. So why is this formula? Again, the number of ways, just to underscore this, the number of ways that we could have picked 4 of the letters from the word central is 840. Now why is this the right formula? Well, it's almost as though we're following the same procedure we did before, but stopping short. Because you can imagine picking the first letter, picking the second letter, right? Because we need to pick 4 letters, and picking the third letter, and then picking the 4th letter, and stopping there. We stopped the process before we picked the 5th, 6th, and 7th letters because we only wanted 4 of them. So from among the 7 letters we had to start with, we only had to pick this 1st, 2nd, 3rd, 4th letters that could be done in 7, 6, 5, 4, respectively, different ways. So this formula for permutations actually comes from the multiplication formula too. The multiplication rule. It's just like a process like this one where you don't go all the way through and do every single pick. So computing permutations, this formula should not be a very mysterious one because it's like a truncated version, an abridged version of this process here, where you start out by choosing objects, but you stop at a certain point. So we're going to move to, again, if this is not making sense to you, make sure that you pause the video and go over these examples and the definition of permutation, consult your textbook. if you get a chance to do that before we continue. We're going to look at one more example involving the multiplication rule, and then we'll look at the idea of a possibility tree, which is a really powerful tool. I don't know to what extent the audio is capturing my dog. Now that the weather's really nice, she's outside a lot, and she is very territorial. Wants to make sure that random miscreants like passersby and children and dogs, I think she's being very protective, especially in the era of COVID-19, and keeping people away from our house. So you can probably hear her in the background quite a bit in these videos, and I hope my voice is carrying better than hers is. Alright. One more example involving the multiplication rule. Let's just use this to count something else. Example, a license plate must begin with a 3-letter string followed by, and to be clear, and be followed by a 4-character string of digits. So our license plate starts with a 3-letter string, like AAA, AAB, AAC, and so forth. And that's followed by a 4-character string of digits from 0 to 9. So it could be 0, 0, 0, 0, 0. It could be 0, 0, 0, 1, 0, 0, 0, 2, and so forth. The question is, how many license plates are there? And here we're assuming these are the only restrictions. So there are no other restrictions placed. You could repeat characters, unlike in the rearrangement of the letter central, or the word central, where you couldn't repeat characters. Now you're allowed to repeat characters, but there are no other restrictions besides these. So the multiplication rule says that we look at the number of ways of completing, I'm going to call it a 2-step process. First we pick our letters, and then we pick our numbers. And you can break this down into a 7-step process if you want to, picking each number, or rather each letter, 1, 2, 3, and then picking each digit, 1, 2, 3, 4. But I'm just going to lump the letters together because I think we're starting to see how this works. So how do we pick our letters? Well, there are 26 choices for the first one, 26 for the second, and 26 for the third, because now we're allowed to repeat. So this can be done in 26 cubed ways. Notice I did kind of break it down in my head into a 3-step process where I picked the first letter 26 ways, times the second letter in 26 ways, times the third. Similarly, we can argue there are 4 different digits we have to pick. The first one picked in one of 10 different ways. The second one also in one of 10 different ways. The third and the fourth. So we multiply those together to get the number of ways of picking the entire 4-character string. And now that we have these individual steps of the process, so the total number is going to equal the number of ways of the first step times the number of ways of the second step. And this is a big number that I didn't even bother to work out. 26 cubed, hold on one second here. Let me figure this out. So this turns out to be 175,760,000 different ways. So if there are no other restrictions on your license plates, that is the number of ways of coming up with a license plate. So go ahead and pause, make sure you understand how this example differs from the previous one, mostly in that you can repeat characters, unlike in the previous case, but they're both dealing with a multiplication rule. Now let's let's see. In these cases, it was pretty easy to keep track of the steps of the process, but your textbook gives an interesting set of examples where it might be a little harder to keep track of all possible outcomes and to even know when you've reached the end of the process. So, your textbook gives the example of a tournament in which two teams are playing, and I think the example your book gives is where two teams, A and B, play until either one team wins 3 games overall or 2 games total. So I'm going to go over that example. I was thinking about making it a little harder, a little more complicated, where a team would have to win 4 games total or 3 in a row to win the tournament, but it turns out the number of outcomes is ridiculous, and I would take a lot of time to go through that example, and I don't think it's any more illuminating. So what we're going to do is draw a possibility tree for a tournament between A and B, where a team wins if, hey, yeah. So my wife is about to take out the recycling. Where a team wins if it wins 3 games total or 2 in a row. And the idea of this might be that they have momentum. They're proving themselves a superior team by demonstrating not that they win 3 overall, but that they have 2 in a row under their belts. So here's how it's going to look. We're going to start with game 1. And look at the 2 possibilities, A and B. Of course, at the end of game 1, neither of these conditions can possibly hold, so we haven't reached the end of the process. So no matter which of these possibilities is followed, we have to follow it with game 2. And from each of the possible outcomes of game 1, we look and see what happens in game 2. All right, now for game 2, we do have some outcomes. A wins if A has won the second game followed by the first one because he has now won 2 games in a row. However, if B wins, A and B have each won 1, but not 2 in a row. Now we play a third game, in game 3. So you can see how I'm kind of, I'm going to use a different color for this. You can see how I'm kind of considering, I'll try to get these to line up a little better. You can see how I'm kind of considering, I'll do this in a different color. Considering the game's sort of on the horizontal axis and the outcomes are sort of on the vertical axis. Now what happens here? If A wins, then we still have no outcome yet because A will have just alternated wins with B. It hasn't won 3 yet, but now B has won the tournament if B wins because now it's won 2 in a row. Now again, in this possibility we have to go to you guessed it, game 4. Now in game 4, if A wins again, then A wins the tournament. If B wins again, however, they have now alternated down their wins, and we have to go to, my goodness, you guessed it, game 5. Oh, I'm losing order here. So I think in this case, whoever wins, so I want to be consistent with my notation here. If A wins, they have now won 1, 2, 3 games, so they'll win the tournament. If B wins game 5, they'll have won 1, 2, 3. So in that case, B wins the tournament as well. We have finally reached an end in this initial branch of this possibility tree. You can see how we carry this out until one of the outcomes is achieved, and we just kind of keep track of what that outcome is. We're keeping track of all possibilities, and that's why this is called possibility tree. We can follow a similar logic for this lower branch. So we have achieved no outcome after the first game, so we look and see what happens in the first 2 games. Well, actually we did, B wins in this case down here because they won 2 in a row. If A were to win after B, we play a third game. A wins if they win 2 in a row. But in the case we have B, A, B, we continue because neither one team has won 3 or 3 in a row. So we continue for a fourth game. In the case of B, A, B, A, there's still no outcome, but in the case B, A, B, B, B wins because they've now won 2 in a row. So finally we play a fifth game in this one case. And we achieve an outcome no matter what. So you can tell a lot from this tree. You can ask the question, for instance, what is the largest number of games played? So the largest number of games is going to equal the longest chain. 1, 2, 3, 4, 5, for instance. There are several, but 5 is the longest number of the longest length of the chain in this tree from our initial starting point before we've played any games out to the end. We had 5 games. What is the probability that 5 games are played? So now we go back to what we were talking about in section 9.1. We look at the number of ways in which the outcome involved 5 games divided by the total number of outcomes, the sample space. So in this case, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different outcomes, and we see 1, 2, 3, 4 of them involve playing 5 games. So 4 out of 10, or 2/5. So we have a 40% chance, 40% probability of playing 5 games. Likewise, we only have 1, 2 out of 10, a 20% chance of playing 3 games, and the remainder are made up of, 2 games. And the remainder, let's see, there are 2 ways, also a 20% chance of playing 3 games, and there are 2 ways of playing 4 games. So all the other possible numbers of games played have the same likelihood, but the highest likelihood of any single number of games played is 5. This is if the teams are equally balanced. You can also see some interesting things. Let's ask the question, what is the probability that A wins the tournament if A wins game 1? This is an interesting question, and in fact, if you look at the history, a lot of probability arose because people were trying to decide answers to questions like, well, let's say we start a tournament but we're unable to finish it. What is the likelihood if someone won the first 3 games that they would end up winning the whole thing? Believe it or not, there were a bunch of French mathematicians in the 17th and 18th centuries that were going about trying to settle gambling problems. And those were the sorts of problems they were asking. And that's why a lot of modern probability came about initially. Of course, it's much more useful than that now. But if we want to know what the probability that A wins the tournament given that they win game 1 is, we look at all of the outcomes that involve A winning game 1, and that would be everything along this first branch. Look at all the possible outcomes. Our sample space is when A wins game 1. So we're really just confining ourselves to the top half of this chart, this possibility tree. And we're counting those in which A wins from among those. So there are 1, 2, 3, 4, 5 outcomes where A wins the first game, and in 1, 2, 3 of them, A wins the tournament. So a 60% chance. If A wins the first game and these teams are evenly matched, then there's a 60% chance that A will end up winning the tournament. Things are a little bit different if we assume that teams are not evenly matched. And I'm going to change this picture a little bit. So make sure that you pause the video and make sure you understand the answers to these questions and all of what's come before you unpause, and you'll see how I'm going to change the tree a little bit to handle the case where maybe Team A is a little bit better than Team B. All right. So let's ask a slightly different question, or let's ask the same questions in the following context. Let's assume now let's go ahead and assume Team A is a little bit better than Team B. Possibility trees can be turned into what we could call probability trees really easily. So let's assume now that Team A wins a game 60% of the time. And Team B 40%, right? They win whenever Team A doesn't, so they'll win 40% of the time. What we can do is we can take this possibility tree, and it's like we're going to add to the tree. I'm not going to draw it on every branch because it gets tedious, but imagine that every time we have a win by A, that branch is followed 0.6, 60% of the time. And a win by B is followed 0.4 of the time. This is what's called a weighted tree or a weighted graph, and we'll talk a little bit more about that in a couple of weeks. But the number on each of these branches, again, this would continue in the bottom half. I just don't want to belabor it or clutter up the graph too much. The number on each of these branches indicates how likely it is that we follow that branch. Now, using the multiplication rule to follow a branch means to multiply the likelihoods, to multiply the probabilities on each branch. So, for instance, if we want to know the probability of this outcome, that A wins in exactly 2 games, we would multiply 0.6 for the first following the first A times 0.6 for following the second A. And so that would happen 36% of the time. 0.36 is the probability we follow that branch. The probability we follow this branch here would be 0.6 times 0.4 times 0.6 times 0.6. And that would give us a different probability, a much smaller one. So this outcome has a lot smaller probability than this outcome does. In the previous example, by the way, that was the example where all of the probabilities were equally likely. In other words, you had a 50-50 chance, a 0.5 chance of following each edge. And you could see that the numbers we got would work out exactly as though we were multiplying those values together and adding up all the probabilities. So, what I want to ask now is the same questions I asked a moment ago. What is the probability? What is the probability that we play the largest number of games now? As we saw, that probability, or that number of games, is 5. Before we saw, we had a 40% chance. Now let's see how this assumption changes that. So, the largest number of games are by following this path, this path, this path, and this path. So what we want to do is we want to do 0.6 times 0.4 times 0.4, 0.6 times, 0.4 times 0.4, and that gets us to there, times 0.4 again. And now, notice that we're going to be adding this branch and this branch. So ultimately what we're going to be doing is going to be multiplying by 1. If you distribute the multiplication and group the 0.6 and the 0.4 together, you'll get 1. So we can actually stop that computation there. But to that, we're going to add the probability of following this branch and the one right below it. And that's going to be a 0.4 times a 0.6 for the second win by A, times another 0.4 for the second win by B, times another 0.6 for the second win by A, and then the same argument at the end here. It's just going to add up to 1 anyway. So if I add these numbers together, I'll do this really quick with my calculator, we'll get the new probability of going to 5 games, which is going to be different from our previous probability. I'm getting for the top number here, I'm getting 0.0384. So one of these two possibilities was an outcome only about 4% of the time if you round off. And then for the second one, I'm getting, you can tell it's going to be a little bit larger, 0.0576, or about a little over 5%, almost 6% chance. So if I add those two together, I get a 0.096 or a 9.6% chance that we go to 5 games. And you might say that's a dramatic change. But what you're doing here is you're saying Team A is pretty considerably better than Team B. They'll win 6 out of 10 times. So the likelihood that B holds on to win, either by winning 2 in a row or by winning 3 games outright, is pretty small. It's a diminishing chance that B is going to take it to 5 games because A is a stronger team. So we went from a 40% chance of playing 5 games to a roughly 10% chance of playing 5 games. I'll leave it as homework to you to figure out the other question we asked, which was the probability that A wins, given that it wins the first game. And just a little intuition should tell you that since A is a stronger team now, it probably has a higher likelihood of winning, given that it wins the first game. So your number should turn out to be, I don't remember, what was it before? Was it 60% chance of winning, I think, if A wins first? Your number should be better than 60%, probably considerably better. So go ahead and pause it right there and make sure that you're understanding this. I know this is a lot to take in. If you have any questions, please check in with me on my virtual office hours, 9 to 10 on Monday and Wednesday. Check in with Steven, he's great. Check in with the Math Lab, they'll be able to help you with this stuff. I'm going to erase here and write down a quiz real quick. This will be quiz CE6. Dealing with some of these permutations and the like. So here's a pretty basic quiz. Quiz CE6. What is the number of permutations of 3 objects from among 5? So how many different ways are there of selecting 3 objects if you're given a collection of 5 objects to choose from? Thank you so much. I hope this makes sense. And again, I look forward to helping you with our class, with anything that I can do to support you in these times. Just send me an email, come to my office hours, and I'll talk to you soon.